This lesson is going to cover single replacement or single displacement reactions. You may see it written both ways. It's the same thing, it's just different terminology depending on where you see it. Previously, we've looked at double replacement reactions when we were talking about precipitation reactions last week. In a double replacement reaction or a precipitation reaction, we have two compounds or two salts that were added together, and then two of those elements swapped places to create two new compounds. In a single replacement reaction, it's going to be very similar, but we're just looking at one element that's going to be replacing an element in a compound. So here's the definition, and there's a little picture to kind of help explain it. So if you'd like to just kind of write down this, I call it a sample equation. It's just kind of a way to explain what's happening by using an actual equation than using a definition. So what's happening is we have a single element here, we'll call it A, and then we have a compound. So remember, anytime you have two or more elements bonded together, we have a compound. And what happens is this single element is going to kind of bump one of these elements out of our compound and replace it. So it's called a single replacement reaction because you have a single element that's replacing something else in a compound. Here you have a picture. It's kind of like dancing partners. Partner A kind of jumps in and bumps out person B. So now B is left alone and A and C are dancing together. There's a few things that are important in when we're looking at single replacement reactions. And there's a few things that we just want to make sure that we do so that we don't write the equation incorrectly. One thing is you always want to make sure that your two reactants yield two products. So if you start with two reactants, you're going to end with two products in a single replacement reaction. There's going to be some rules that we're going to look at on the next slide. This also on your reference sheet that that's uploaded to Schoology, so you can double check that as well. I'd have that available. So let's look at an example here. So in the lab that you just completed, a little simulation, you were looking, or in the video lab, tomorrow you'll do a simulation. In the video, you noticed how certain metals were much more reactive than other metals. Like for example, calcium reacted vigorously with water as well as with acid, lots of bubbles and a very bright pink color immediately. Whereas aluminum or iron, some of the other metals, they weren't quite as reactive as calcium. And so you should have been able to kind of put those in order of how reactive they are. And when you did that, we have what is called an activity series. And I'm just going to scroll down real quick and I'll go back up. So here's our activity series, and this is also listed on your notes page. It can also be found on your reference sheet that's in the back of the lab manual. And again, it's uploaded to Schoology as well. So this is just a nice little chart that lets us know how reactive a metal is. So the most reactive is at the top, and our least reactive is at the bottom. And you'll notice the most reactive reacts with cold water. As we go down, we're not really reacting with water anymore. It might react with oxygen, but it might be a slow reaction. And then we have virtually unreactive metals down at the bottom. So when we're looking at a single replacement reaction, it's important that we're checking our activity series as we're that we're doing is once we're sure that this reaction is going to take place, this is kind of what you're going to do, the steps for how you'll write your reaction. So the first thing you want to make sure you do is you look at your charges for each part of your equation for 3 different elements. And then when I'm trying to decide what's going to replace what, I always want to make sure I'm swapping like with like. So like, for example, since magnesium is positive, has a positive charge, I want to make sure it's going to swap with the positive element in this compound. So if it's positive, the cation is going to swap with a positive cation. If it's an anion, it's going to swap with an anion. So you always want to make sure you're swapping like with like. And you can't do that unless you've looked at your charges. So that's what you're going to need to do first. Usually your new lone cation or anion, whatever it is that's now been kind of bumped out of the way, you're going to write it as diatomic most of the time. Now, sometimes you won't. There are some that are not, you won't have to do this with, but there are 7 diatomic elements. So you'll need to kind of memorize these. It's fairly simple to kind of remember. I put them in order and I made a word. So it sounds kind of funny, but it's Brinckerhoff. If you just say that in your head a couple times, then you can kind of remember these words. If you look at a periodic table, if you notice a lot of these are halogens, which is in that group 17, and it kind of makes like a little 7. If you look, because you have like oxygen, nitrogen, fluorine, and then you have chlorine, bromine, iodine. So you kind of have them listed in this little 7 shape, and then you have hydrogen, which is kind of over there on the other side that you'd have to remember to include. But if you can just remember Brinckerhoff, it'll kind of help you remember which ones are diatomic. Diatomic just means that di means 2, so 2 atoms. It just means that they like to bond to themselves. They're not very comfortable, right? The whole point of bonding is to fill that outer shell. They want to be able to do that, and so they end up just bonding to another atom just like they are, and then that gives them that full outer shell. So they're just called diatomic elements. They're never going to be found alone in nature. They're always found bonded to themselves. So when you rewrite your equation, since hydrogen was kicked out, right? My magnesium kicked out hydrogen. Now hydrogen's alone, but I have to make sure I'm writing it with the 2 subscript because it's diatomic. One thing, I would make sure I highlight this in your notes. When H2O splits, you're going to need this later. It splits into a H plus and an OH. I know this is different than what you're used to looking at because you're used to thinking the charges crisscross, and that is always correct. The reason that this is H and OH is because it's really, water can function as an acid or a base, which we're going to talk about later in the week, and that's why it separates into hydrogen and hydroxide ions. It has to do with its acid-base function. So just kind of highlight this so you remember. So we have some rules, and what we're going to do is we're just going to work an example for each of these rules. That way you can kind of see what they mean. So we'll talk about them as we get there. So again, we've kind of already gone over this. One thing we want to look at before we kind of do any work is to make sure we're actually going to have a reaction. So will magnesium replace the hydrogen in HCl? Okay, so magnesium has to be able to replace it. So what I'm going to do is look, here's hydrogen down here on the bottom. Remember, it's diatomic, so it's going to be listed as H2. And here's magnesium. So because magnesium is higher up, it's more reactive, so that means yes, the reaction will occur. Okay, if I look at magnesium and sodium, well, there's magnesium, and then sodium is actually above magnesium. So what that means is magnesium is not reactive enough. It's not strong enough to kick sodium out of the way. Sodium is more reactive, meaning that sodium's going to hold on to chlorine tighter, basically. It's kind of a way to think about it. And it's not going to let magnesium replace it. Okay, so in this case, you would write no reaction. Okay, because magnesium is not strong enough or reactive enough to remove sodium. So let's look at this first rule. This is just a metal replaces a metal. So I'm using the activity series. Nothing real fancy is going on. I'm just going to look and see if I can, if this reaction will occur, and then I'm just going to rewrite my compound. So again, I need to look and see my charges. So I'm going to look on my reference sheet. Sodium is 1 plus, iron is 3 plus. So I know that sodium is going to try to replace iron because my positive is going to replace my positive. So I need to look and see. So there's sodium, and here is iron down below. So yes, a reaction will occur because sodium is higher up. So now, instead of sodium being by itself, iron is by itself. And then it's sodium. Remember, sodium has a 1 plus. Bromine has a 1 minus. And so when I crisscross my charges, remember they're going to cancel out. So I'm just going to write it as NaBr because my ones are invisible, right? I don't have to write them. Okay. I'm not going to balance it just for the sake of time, but you would need to balance the equation. So let's do a we do. I suggest pausing here. Try this one. Okay. And see if you can figure it out. So iron, funny, I didn't give you a charge because it's an equation. So I think originally that I had this in a word and I changed it. So let's pretend iron is 2 plus just for sake. I know lead is 2 plus because the subscript 2 down on the bottom. I can look at my polyatomic ion sheet and I know that NO3 is nitrate. It's a 1 minus charge. So it is iron is going to try to swap with lead. Let me look and see. Iron is up here above lead. So yes, a reaction will occur. So now that means lead is by itself. My iron, let me write it down below so we can see. So I don't have to erase it. Iron, remember, is a 2 plus. NO3 is a 1 minus. When I crisscross my charges, I'm going to have an invisible 1 down below and a 2 down below here. So my iron, remember I have an invisible 1. Then when I write my NO3, the 2 is going to crisscross down, but it's not NO32. Remember, I have to use parentheses around my nitrate, NO3. Okay? And again, you would balance the equation. Let's look at number 2, rule number 2. So we're talking now with water. A lone metal is going to replace the H in water. Okay. And again, this hydroxide, what that's talking about is the OH, because water is always going to separate into H plus and OH 1 negative, 1 minus. So hydrogen has a 1 plus, hydroxide has a 1 minus. Okay, and then hydrogen gas, remember, is just that diatomic element, hydrogen. So when I'm looking at my activity series, I just want to make sure that sodium will react with water. So let me find sodium. It says it reacts with water, so I'm good to go. So sodium is going to replace hydrogen. Okay, and remember, it's going to make a metallic hydroxide. So I'm going to have Na, sodium, which is a 1 plus, remember, and it's the hydroxide 1 minus. So I can think of it like if sodium has the 1 plus, instead of another way to write H2O would be like writing HOH. So when my sodium replaces the hydrogen, it's left with the OH that it'll bond with. Okay, and because they're both ones, they're both invisible. So it's just NaOH plus, and again, hydrogen gas is just H2. Okay, let's look at calcium. So I suggest pause here, make sure your reaction can take place, and then write out your new products. So hopefully you've tried it yourself. Calcium, I'm just going to look. Here's calcium. Again, it reacts with water, so I'm good to go. I can think of this like H1 plus, OH1 minus. Calcium has a 2 plus charge because I looked at the periodic table charge sheet. I'm replacing the positive hydrogen, so I'm left with calcium 2 plus is now bonded with OH 1 minus. When I do my crisscross, okay, calcium, the 1, it's going to drop down and be invisible. The OH, the 2, is going to drop down. But because this is a polyatomic, I want to make sure I use my parentheses because it's not just 2 hydrogens, it's 2 entire hydroxides. Plus hydrogen gas, H2. Okay, and that's all that I have left, right? Because hydrogen was kicked out of the water. The reason we write H2 is because it's diatomic. Rule 3 is we're looking at, again, a metal, always metals. And this time, instead of reacting with water, it's going to react with the H in an acid. So an acid is just anything that starts with H. So here I have, this is hydrobromic acid, hydrochloric acid, hydrofluoric acid. Notice they all start with an H and then they just have an ion. So it looks like a regular compound. It's not really anything different than what we've done before. The reason it just has its own rule is because you're looking to make sure that it'll actually react with an acid in the rule. And notice everything that's above where hydrogen is will react with acids. So aluminum, where is aluminum? It is up here. It says it will react with acids, so I'm good to go. So it's going to replace the H. So I have aluminum, which is a 3 plus, Br, which is 1 minus. So when I do the crisscross, right, I end up with Al1 and Br 3 because the 3 from aluminum crosses down. Plus, again, I'm left with hydrogen gas, which is just H2, which makes sense because I kicked the hydrogen out. It's the only thing that's left by itself. Again, I'm double checking. I have 2 reactants. 1, 2. I have 2 products. 1, 2. Okay, if you only have 1 product, something's missing. Let's look at copper. Copper, will it replace the H? Does copper react with acids? Look down here. Copper is down here below hydrogen, and there's no react with acids. So this reaction will not take place. No reaction. Okay, or NR, whatever you want to say. Okay, so try this one. Try your magnesium. Again, you're going to look at your charges on your periodic table. I'll go ahead and give you those just to speed it up. So pause here. Try to see if you can swap that around. Because yes, magnesium does react with acids, so we're good to go. All right, so if you tried it, you know your magnesium is going to replace the H. That's what our rule tells us. So we're going to have Mg, which is 2 plus, and an F, which is a 1 minus. When I crisscross my charges, the 1 is going to drop down by magnesium, right? But it's going to be invisible. And then the 2 is going to drop down by fluorine. So if I rewrite that correctly, remember the 1 drop down and then the 2 drop down. Plus, hydrogen was kicked out. It's diatomic. I write it H2, hydrogen gas. So your rule basically tells you what to write. A salt is any kind of compound that has a positive cation and a negative anion. That's all a salt is. All right, last rule. This one, instead of looking at a metal, now we're looking at halogens. So halogens are this last group 17, like your chlorines, bromines, iodines, fluorines. Okay, those are our halogens. And they have, they're reactive differently also based on where they are. And this all kind of goes back to when we talked about ionization energy, right? How good are they at bonding? How good are they at taking electrons from other elements, right? How good are they at that? So I just have to look and see, same thing. This time, I'm still going to look at my charges. Since fluorine is an anion, a negative, when it swaps, it's going to swap with the bromine instead of the sodium because we're getting like swaps with like. So I need to look and make sure that fluorine is actually above bromine, and yes it is. So here's fluorine and here's bromine. So fluorine is more reactive. Okay, so I'm going to have Na, which is 1 plus, and instead of bromine, my fluorine is going to go in there, which is a 1 minus. Notice I'm not bringing the 2. The 2 is only there. This 2 is only there because fluorine is diatomic. When I write it by itself, it needs the 2. When it's written with another element in a compound, it gets its number based on the charge. Since these are both 1s, they're going to crisscross. They're invisible. So my formula is just NaF plus what I kicked out was Br. Remember, this is diatomic, so it's 2. And if I forget, it's written as Br2 in my chart as well. Okay, so here I'm going to look here. Bromine is going to swap with chlorine. I know that because I'm looking at my charges. My anion is going to swap with my anion, negative with negative. Is bromine more reactive than chlorine? No, it is not. Bromine is below chlorine. That means no reaction is going to occur. Okay, because bromine is not strong enough or not reactive enough to kick chlorine out of the way. Chlorine is more reactive. It wants to bond to magnesium more. It has a higher ionization energy, so it will not react. Okay, so try the we do, and then I'll go over it once you're done. And again, you will need to pause. So I've written my charges. I know chlorine is going to try to replace fluorine because they're both negative. Chlorine, is it above fluorine? No, it is below it. So there is no reaction. Okay, so it's smart. You want to go ahead and look at your activity series before you start doing all the work. Once you know what it's going to swap with, look at your activity series. Otherwise, you're going to do a whole bunch of stuff that you don't have to do because no reaction takes place. Okay, so I'd like for you to pause the video here. Try these yourself. And then you can start the video back and check your answers. And I've given you a spot to check your rule number just so you can kind of focus, what you're going to be doing. So pause. I'm going to work them out very quickly so you can kind of check your answers and then you'll be done. So chlorine, Cl, chlorine. I know that chlorine is a halogen, so I'm going to be looking at Rule 4. A lone halogen. So I look at my charges. Chlorine is going to want to replace the other negative, which is iodine. I look, chlorine is above iodine, so it's more reactive. So I have Na, again, which is a 1 plus. Cl is a 1 minus. When they crisscross, the charges are invisible. And then I'm left with iodine by itself because it got kicked out. It is diatomic, so I'm going to write I2. If I forget, it's listed as I2 right there as well. The next one, HCl. Anything that starts with H is an acid. So I'm looking for the rule with an acid. That's rule number 3. It says the metal is going to replace the H in acid. It's going to make salt and a hydrogen gas. Remember, salt is just a positive ion and a negative ion. Doesn't matter what it is. So I want to look. I know aluminum has a 3 plus charge. Hydrogen has a 1 plus. Chlorine has a 1 minus. Aluminum, like the rule says, is going to replace the H. Aluminum reacts with acids. Check. So Al, 3 plus, Cl, 1 minus. When I crisscross my charges, the 1, invisible 1, is going to come down here. The 3 is going to drop down here below chlorine. Let me rewrite it. AlCl3 plus, what does my rule say I'm going to make? Hydrogen gas, which makes sense because that's what I kicked out. Hydrogen gas is always H2 because it's diatomic. Next one, zinc and water. I'm going to look at the rule that looks for water. That's rule number 2. Zinc is a 2 plus charge. Water is a 1 plus, or hydrogen is a 1 plus, and remember water separates into hydrogens that are 1 pluses and OH that's a 1 minus. So when zinc replaces the hydrogen, it's going to be bonded with the OH. When I crisscross, I'm left with zinc, an invisible 1. This 2 is going to crisscross down here. Remember, I can't just leave it OH2 because it's not just 2 hydrogens. It's 2 hydroxides plus hydrogen gas because I kicked out the hydrogen. Last one, metal replaces. This is nothing special. If I'm trying to figure out what rule, I know it's not water. I know it's not acid, and I know that iron is not a halogen because it's not, my halogen chart is right here on the top. So I know that this is just rule number 1. Let me look at the charges again. Iron is, let me tell you, it's 2 plus. Silver is 1 plus and chlorine is 1 minus. I need to look and see if iron will replace silver. And iron is, let's see, silver is down here and iron is right here. So yes, iron is above silver, so I'm going to have a reaction. So silver is just kind of by itself, right? I've kicked it out. And then my iron, which is 2 plus, and chlorine, which is 1 minus. When I crisscross, I'm left with FeCl2. So hopefully you did okay. If not, please reach out to your teacher so you can get additional help